everybody. So I'm going to preview for you day 21A, which is part A of set 7, and we're also going to look at 22A, which is set B. And we'll take a look at a few questions from each of the Mathia sections. Okay, so let's start with the first one, which was on modeling ratios as rational functions. All right, so we're going to go through the step-by-step example, and then we'll try one other problem. So let's move this out of the way so we can read the problem. In basketball, a player's free throw percentage is the ratio of the number of completed free throws to the number of attempted free throws. Ben has attempted 39 free throws so far this season and has completed 12 of his free throws. A teammate challenges Ben to make every free throw shot in a row or consecutive shots for the rest of the season. Define a variable for the number of additional free throws made. Then use this variable to write an expression for the free throw percentage. Any percentages should be written in fraction or decimal form. Okay, so we see this table here. We've got an expression for the number of additional free throws. So we need to define some sort of variable. So what kind of thing can we use? Let's try just x. Okay. Then we have the number of completed free throws. So the number of completed free throws consists of the number of free throws completed so far, which is given, and we're going to add to that, so plus the number of additional free throws. So let's see, he's attempted 39 and he's completed 12. So let's do 12 plus x to see if that works. It does. Okay. The number of attempted free throws, well, he already attempted 39, but he's going to attempt x more that he's going to make every single one of those, right? So we're going to do 39 plus x. Okay, and so we need to write a ratio to create, or a percentage. We're going to do a little division. Okay, so let's divide the number of completed free throws. Oops, let's do the division first. So we can type the whole thing, 12 plus x, divided by 39 plus x. Okay, so now question 1 says, what is Ben's free throw percentage so far this season before making any additional free throw attempts? So basically there's no more additional free throw attempts, so we're going to let x be 0. Okay, so this is going to be 12 plus 0, or just 12. This is going to be 39 plus 0, or just 39. And this is going to be 12 plus 0. I mean, you could write it as 12 plus 0 divided by 39 plus 0. Basically, I'm plugging in x with 0, or I could just do 12 over 39, and there's our decimal. So the second one says, how many consecutive free throws must Ben make to have a free throw percentage of 0.64? So we're filling in this table the free throw percentage first. So we're going to type in 0.64. Okay, the solver will be started for you this time. So what they're doing is they're going to solve for x. Basically, what we could do is we could set 12 plus x divided by 39 plus x equal to 0.64. Okay, and this is the equation in the yellow right here. Use the solver to set these values equal and calculate the value of x and the number of additional free throws. Okay, so enter the equation. 0.64 equals 12 plus x divided by 39 plus x. And they solved it for us, it looks like. Oh, wait, no. Just kidding. All right. We have to do the solver part. Okay. So what I would do is I would multiply both sides by 39 plus x. because it's in the denominator, we would want to get it out of the denominator. And that's exactly what they say. If we multiply both sides by 39 plus x, the right side will reduce to eliminate the denominator. So we're going to click multiply both sides. We're going to do 39 plus x to both sides, push enter, happy, happy. So then one side it cancels, and so now we're going to have to do a little distribution. We're going to distribute the 0.64 to the 39 plus x. All right, now I have x's on both sides, so let's subtract 0.64 x from both sides. Okay, and now I'm going to have to get rid of this 12. I'm basically solving a linear equation here, so I'm going to subtract 12 from both sides. And then I'm going to divide both sides by 0.36. And we get x is 36. And that's a good sign because x should be something that is a whole number because it is a number of free throws. If you get a decimal or a negative, that doesn't make sense for this situation. Okay. So we found this was 36. This is going to be 12 plus 36 or 48. This is going to be 39 plus 36 or 75. Okay, now we're on to question 3. Move this out of the way so I can see it. What is Ben's free throw percentage if he completes 18 consecutive free throws? Okay, so 18 is our x. Now we're going to do 12 plus 18. I mean, obviously you can add these, but Mathia will add them for you. 39 plus 18. Excuse me. And then we're going to do 30 divided by 57. And there's our percentage. Okay. Let's do one more problem from this. Your problem will vary, of course. Okay, but it's a similar situation. So in our problem, Irene is at a golf course to practice her putting game. So far, she has made 10 putts out of a total of 19 attempts. Ooh, sounds familiar. She wants to make all of her putts for the remainder of the practice season. Define a variable for the number of additional putts made, then use this variable to write expression for the percentage of putts made. Okay, so it's very similar to the last one. Instead of free throws were putts. Okay, so let's call the unknown number of additional putts x. The number of putts made, let's see, she already made 10. We're going to add the x. She already attempted 19. We're going to add x, and then we're going to divide it. We're going to 10 plus x divided by 19 plus x. Okay. Question 1, before Irene attempts any more putts, what is the percentage of putts she has made so far? So we're not going to attempt any more, so we're going to make that 0. So that's 10 and 19 because we're just adding 0. And this will be 10 divided by 19. So she's made 53%. Okay, question 2. How many consecutive putts must Irene make if she wants a percentage of putts made to be 70%? So we're going to go over here to percentage, and we're going to not type it in as a 70, but a 0.7. Okay. But we're not done. It jumped us to this one, but we're not done. We got to, we have to set up an equation here, don't we? We're going to take 10 plus x divided by 19 plus x and set it equal to 0.7. So we can use the solver. Here's the equation we're going to solve. 10 plus x. I got to divide first. Otherwise, it just divides the x. 10 plus x divided by 19 plus x is equal to 0.7. Okay, well, that's what we're going to solve. Let me move the solver so I can see it. So you're going to want to multiply both sides by the denominator, which is 19 plus x. Then we're going to distribute. It distributed, it's so convenient. Let's subtract from both sides the 0.7x here, so we can get our x's onto the same side. Then I'm going to move this 10 to the other side. I'm going to need to subtract 10. And then I'm going to need a little division, so we're going to divide both sides by 0.3, which was the coefficient of x, and we get 11. All right, let's move that down. So we know it's 11. This is going to be 10 plus 11, 21. And this is going to be 19 plus 11, which is 30. Okay, question 3, what is the percentage of putts after Irene, if Irene makes 16 consecutive putts? So that would be 16. And then we add 26. And then 19 plus 16 is 35. And then we do 26 divided by 35. Okay, and we're done. All right, let's go ahead and take a look at the next workspace. Okay, so this one's using rational models. All right, let's read the question before we get into this. So Jeffrey is watching a lightning storm that is 6.8 kilometers away from his front yard. He remembers from science class that the speed of sound depends on air temperature. This relationship can be modeled by the formula T equals 1000 times 6.8 divided by 0.6 C plus 331, where T is the time in seconds it takes for the sound to travel 6.8 kilometers, and C is the air temperature in degrees Celsius. Oh, fancy formula. Define a variable for the air temperature. Then use this variable to write an expression for the time it takes to hear thunder after seeing lightning. Okay, so this air temperature, we can use, so that's what, C. Okay, and then at time it takes, we're going to use this expression, 1000. Let's do the division first because there's a lot going on. 1000 times 6.8. And then in the denominator, we are going to have 0.6C plus 331. Just copying it. Push enter. Here we go. Okay, so question 1 says, Jeffrey sees lightning strike and 17 seconds later he hears the thunder. What is the air temperature? So this expression represents the time it takes to hear the thunder. So he heard 17 seconds later. So we're going to put a 17 here. And we're going to have to set this expression equal to 17. And so we're going to make an equation. So we're going to go to the solver. Okay, so we're going to do 17 equals 1000 times 6.8 divided by 0.6C plus 331. So just like with the other one that we just did, we've got to get rid of this denominator. Let's go ahead and maximize this. So we're going to multiply both sides. It says, rewrite the equation with the fewest possible factors. Okay. So let's multiply both sides by that denominator. Okay, so to get that denominator out of there, so we're going to do 0.6C plus 331. That'll cancel it on the right, leaving us with just this 6,800 was 1,000 times 6.8. Let's distribute. Thank you, magic distribution thing. All right, we don't have variables on both sides, but I'm going to subtract 5627 from both sides. Divide both sides by 10.2. And we get the answer was 115. So we're going to move this down. (115°C seems pretty hot. Okay, question 2. Jeffrey sees lightning strike. He looks at the thermometer to see that the temperature is 22°C. How many seconds will pass? So this time they're giving us the temperature. So we're going to put in 22. And then here, I'm going to do 1,000 times 6.8 divided by 0.6 times 22 plus 331. So I'm plugging, oops, I put in 222. That's not going to work. Let's go back and fix that. Okay, and it calculates for me. So this is very similar to the other one that we were doing. I don't think I'll do a second problem for this one. Let's go ahead and we're going to look at tomorrow's Mathia as well. I'm going to give you a little preview of those two. Okay. So this one says a barge is transporting goods from a warehouse to a factory. The barge travels upstream 55 miles to the factory and then returns downstream to the warehouse. The barge travels upstream at a rate that is 6 miles per hour slower than the rate that it travels upstream. The barge's total travel time is 8 hours. Let S represent the average speed downstream. Okay, so we've got expression. We got all these expressions. Quantity description. So the problem tells you that S represents the average speed downstream. So average speed downstream. Okay, easy peasy. All right, what does the 55 represent? So let's read it. The barge travels upstream 55 miles. That is a distance. The miles tells us it's a distance, not a speed or anything. So it's a distance traveled. And it is just upstream, it says. Okay, the 8, where does the 8? The 8 is the barge's total travel time. It's in hours. Time traveled. Now it says total, so I'm going to say for the round trip. So there and back again. Okay, the 55 again. All right. The 55 is distance traveled. I don't know why it's repeating itself, but I'm just going to go with it. And it is upstream. Wait a minute. It goes, wouldn't it be the same both directions? That's why it's repeating. Okay. So if it goes 55 miles upstream, it's going to go 55 miles downstream, right? Because it's going back and forth. So I'm going to say downstream this time. Yes, that's why it was repeated. It wasn't because they just copied it. 55 times 2, well, that's going to be the total distance, isn't it? If you go 55 upstream, 55 downstream, that's going to be distance traveled, but this time I'm going to say it is the round trip. Okay. S minus 6. So you may remember it said the barge travels upstream at a rate of 6 miles per hour slower than the rate downstream. So S was the downstream speed. S minus 6 is going to be your average speed going upstream because it's going to take longer going upstream. So it's slower. Okay. So now look at the worksheet. The expression 55 over S minus 6 was derived using the relation hours equals miles divided by miles per hour. So you got to know the formula like distance equals rate times time. Okay, that's where they're getting this from. Distance equals rate times time. So if you solve the equation for R, you can divide both sides by T. You get another version of the equation, which is rate is equal to distance divided by time. And you could solve for time by dividing both sides by r, and you get distance divided by rate is equal to time. So what we have here, 55 is a distance, so in miles, and s minus 6 was a speed. So distance divided by rate is going to be equal to time. And it's the time traveled. Let's see, s minus 6 was upstream. Yeah. So they took the distance traveled upstream, which was 55, and divided it by the speed upstream, which was s minus 6. And you get an expression for the time traveled upstream. So 55 over s is going to be the time traveled downstream, because s was the speed downstream. Okay, so then lastly, we have the 55 times 2, which was the total distance traveled, divided by 8, which was the total time traveled. So if we look back here, total distance divided by total time, distance divided by time is equal to the rate. So this is going to be the average speed I clicked it. What's happening? For the whole trip. There we go. Just wasn't clicking for some reason. So let's move this out of the way for the next part. The expression 55 over s minus 6 plus 55 over s can be set equal to one of the expressions above for s. Identify the quantity that the expression represents. Well, let's look over here. So 55 over s minus 6 is a time. 55, it's the time to take upstream. This was what this expression was. 55 over s is the time downstream. So if you add those together, it's going to be equal to the total time, which is 8. So this is equal to the time traveled for the whole trip. Come on. There we go. Okay. So enter an equation that could be solved for s. So we're going to take 55 over s minus 6 plus 55 over s and set it equal to 8, and that's what we're going to solve. So they didn't even ask us to solve it, at least in this part. They just want to build the equation here. Okay. This one's just the same as that one. We're going to go ahead and take a look at the next workspace. Okay. So this is the last workspace, which is modeling and solving rational functions. Okay. Before I get into filling things in, let's read the problem. There is a new shark tank at the zoo, and it needs to be filled with water. The shark tank contains a fill hose and a drainage pipe. Using the hose, the tank can be filled in 6 hours. Using the drain, the tank can be emptied in 7 hours. Bianca begins filling the tank with the hose. After 3 hours, she realizes that the drain is open. She closes the drain and continues filling the tank. Use a negative number to represent the rate of filling for the drain and the amount of the tank filled in by the drain. What is the total time it takes to fill the tank? Let T represent the time spent filling the entire job. Complete the table, then use it to write an equation that could be solved for T. All right. Okay, so they're telling us right now the variable T represents the time spent filling for the entire job. So under time spent filling, entire job, we'll just fill in a T. Okay. The rate of filling of the hose. Okay, So the hose is filling it up at a rate of, well, it says in the problem the tank could be filled using the hose in 6 hours. So the rate is tanks out of hours. So that's why they're getting one tank for 6 hours. The drainage pipe says that it can be emptied in 7 hours. And notice they want us to use a negative number represented to represent the rate of filling for the drain and the amount of the tank filled for the drain. Okay, so for the drain, we're using a negative. So it's going to take 7 hours to drain the tank, which is a negative rate of filling. So we're going to do -1 out of 7. Okay. From the problem statement, we know that Bianca closes the drain after 3 hours. Therefore, the time spent filling by the drainage pipe is 3 hours. Okay. The problem statement indicates the number of tanks filled for the entire job. Which I believe is just one tank, right? Yeah, just one. The amount of the tank filled by the drainage pipe is equal to the time spent filling by the drainage pipe times the rate of filling by the drainage pipe. We know an expression for the time spent filling by the drainage pipe, 3 hours. You also know an expression for the rate of filling by the drainage pipe, which is -1/7 tank per hour. Okay, so if we multiply 3 times -1/7, we get -3/7. All right, the time spent filling by the hose is equal to the time spent filling for the entire job. Okay, they're the same. And the amount, okay, so here again, we are going to multiply. Okay, so this time we're going to be multiplying 1/6 times t. We could do t over 6. Okay. And the entire job now. Okay. The rate of filling for the entire job is equal to the amount of the tank filled for the entire job divided by the time spent filling for the entire job. So kind of backwards. So we're going to do 1 divided by t, which is 1 over t. Select a quantity you can define in a different way in order to solve for t. Okay, so select a quantity in which you can enter a second expression that could be used to solve for t by setting the second expression equal to the first. You can enter a second expression for the amount of the tank filled. Okay, so we filled it in with the amount of the tank filled by the hose. And the amount of the tank filled by the hose is equal to the amount of the tank filled for the entire job minus the amount of the tank filled by the drainage pipe. You know an expression for the total amount of the tank filled for the entire job is 1 tank. You also know the expression for the amount of the tank filled by the drainage pipe. So we're going to subtract them. So it's going to be 1 minus -3/7. So now, finally, we're going to enter an equation that could be solved for t. Okay. Well, you already have entered 2 expressions for the same amount. So we've got t over 6 and this thing. We can set them equal to each other, can't we? There we go. All right, I hope you can do well with this Mathia. Remember, I have some available office hours that you can come and we can work through some difficult Mathia problems if you get stuck.